Alrighty then. How about here at the beginning of our study of equilibrium, just a few more thoughts about attaining an equilibrium, getting to an equilibrium, starting at one position and moving to a new position of, I don't want to say balance because it's not necessarily 50-50, but just extra examples. Let's try one here. Nitrogen gas, hydrogen gas, reacts to give NH3 ammonia. Balanced equation 1, 3, and 2. They show a double arrow in the beginning, but this graph is actually imagining taking some H2 gas initially at time 0 and some N2 gas also at time 0 and no NH3 at time 0, but letting them react. So only the N2 and the H2 are reacting in the forward direction to give ammonia NH3 initially in the beginning. But as we learned in the last unit, most reactions go faster in the very beginning and slow down over time. Indeed, this is steeper in the beginning and slows down as we reach this point. Steeper in the beginning here and slows down as we reach this point. You might notice that this graph is about the H2 green line is about 3 times steeper. The slope is 3 times steeper than the N2 because there's a 3 here and a 1 here. And there's a 2 here, so this line is about 2 times steeper in the opposite direction than this one. The ammonia is appearing and levels out here at a certain amount concentration. How much do we have? And the H2 and the N2 are both decreasing. By the time I reach this point right here, I don't know if it's 5 seconds or 50 seconds or 5 years, we reach some kind of balanced state where this forwards reaction slows down and the backwards reaction picks up. This backwards reaction is not depicted here in the graph, but the more of this I make, the more of this could possibly break down to give H2 and N2. So as the forward continues, I build up more of this product, but the product turns right back around and goes back this way. I really could call that a reactant if I go backwards. Interesting. Or I can think about the particulate nature over time and a particulate model over time. Here I have some H2 in white and some I2 in purple, and at time 0 they are certain concentration, certain pressure perhaps, of H2 and I2 and no HI. And in the beginning, the H2 and the I2 react to give a lot of HI, so they go forward to make the HI. In this, after 16 or so seconds, I made a little bit of HI, and a little bit of H2, a little bit of I2 is decreased, diminished, gone away. So perhaps this picture is in this area somewhere. But by the time I reach right here, I've reached an equilibrium of sorts where the concentrations, the macroscopic measured concentrations, are leveled out, and from here on out I don't see much over time. I don't see much change in concentrations. On a particulate level, yeah, indeed, there still is some H2 and some I2 going forward to make 2HI, but there's also 2HI coming backwards to make I2 and H2. So after about 31 or so seconds, according to this cartoon, I reach an equilibrium. So this picture and this picture should have the same quantities, although of course the particles are buzzing around, so they're in different positions. But macroscopically, in terms of sitting on a countertop, I would measure no concentration difference between this one and this one. Interesting. I don't know. I like those pictures. They help me build a model in my mind about the particulates, move the molecules and ions or whatever colliding and moving around. Alright, so this, another cartoon picture. Time goes from 0 here on the left over to something on the right. Wish that arrow was a little bit bigger, whatever. And I have what looks like NO2 particles. Oxygen is usually in red, nitrogen is usually in blue. And they react to give N2O4 particles. So at point B I've only made 1, but at point C I've made a total of 3. And at point D I also have a total of 3 N2O4 particles. Interesting. It's actually arguable that you couldn't have such a small quantity and reach a steady state equilibrium of sorts, but in any case, the question here is which two slides would the forward reaction be proceeding at the most rapid rate? Don't most reactions go the fastest or the most quickly in the beginning? So how about A and B? So between here and here, although I'm having a hard time buying that, because there I only create from between A and B I create one molecule of N2O4, but between B and C I create a total of two more. So unless this time between A and B is different than the time between B and C, it sure looks to me like between B and C is the most rapid rate, if time is linear, depicted linearly in this cartoon. I don't know if I like that after all. Well, I should be careful. We should be careful. Everyone should be careful about how we word these questions. Which slide has the best chance of being closest to a final equilibrium state? Well, I guess I'd have to pick D. Although there's no difference between C and D, I didn't know there would not be a difference between C and D until I looked at the position in D. If I find that D has the same number of N2O4s as C did, then I could say that this cartoon has already reached a steady state and it won't change any further. But I suppose the longer you look for the longer period of time for which you observe, the more certain you are that it's closer to the final state. Although after it doesn't change for 17 days and you're pretty sure you're at an equilibrium state. I just made that number up. Well, whatever. Think about it. Another graph. Here we're looking at reaction rates instead of concentrations. So the rate's fast in the beginning and then it slows down to a certain amount in the forward direction. Then the reverse reaction for whatever it is, I don't know, looks like I thought here maybe perhaps A is 3 times steeper than B, maybe even 4 times steeper than B. But B starts out at nothing in the beginning, but as A decomposes or changes into B, not decomposes, it must be adding together to make B, but then B will turn around and go back and make some A. So the amount of B going in reverse to make A is, the rate is 0 in the beginning and then increases to something steady at the steady, I shouldn't say steady state technically, that's more of a biochemistry and biology phrase. I should stick to the word equilibrium. But the key is this: when the forward rate equals the backward rate, the rate of the forward, and the last unit we talked about the rate constant for the rate law, describing the forward reaction this way, or there's also one for the backwards reaction. But when those rates are equal, then I'm in an equilibrium. Part of the one definition of equilibrium is a reversible reaction that has the forward rate equal to the backward rate. Or you could also say it's something like a reversible reaction containing both reactants and products, same container, where over time it appears as though no net concentration change occurs. What's up with this? Another silly picture cartoon. Let's see. A2B and A2 and B2 are placed in a 1 liter container, allowed to equilibrate, come to an equilibrium. Looks like two A2Bs decompose to give two A2s and B2. And yeah, as time progresses from 1 to 2 to 3, which diagram likely illustrates the first attainment of an equilibrium? I wish we had some more pictures, but I guess I can do it. Here I have, what do I have? I have 1, 2, 3, 4, looks like A2Bs. Here I have two A2Bs, and here also I have two A2Bs. And two purples, probably A2s, and no, I'm a little bit, let's see, A2, A is gold, so this would be 1, 2, 3, 4 A2s, 2 B2s, same story here. So it looks like in picture 2 or cartoon 2, I first have reached an equilibrium. As evidenced by, in frame 3, nothing seems to have changed. So in a more realistic sense, perhaps this is 2 moles of A2B, 1, 2, 3, 4 moles of A2, and 2 moles of B2. I guess moles are more macroscopic than particles. Particles aren't macroscopic, particles are submicroscopic or particulate level. A couple of other things to be aware of that sometimes might be confusing in the beginning. Well, first of all, remember the forwards and backwards rates are equal, and we could also say that the concentrations of reactants on this side and products on this side end up being the same over time. That's when an equilibrium is reached. Although sometimes you'll see the arrows drawn disproportionately. Um, if sometimes you'll see the forward arrow drawn bigger and the backward arrow drawn smaller, that usually means that I'm going to end up with more products on the right hand side than reactants on the left. If the rate of the forward is much bigger than the rate of the backwards, then I'm going to see a whole bunch of the stuff on the right. Conversely, if the Kr, this is the rate constant for the reverse, is larger than the rate constant for the forward, I'm going to see a whole bunch more stuff on the left than I am going to see on the right. Also, in other situations, you'll see the forwards arrow or the backwards arrow, take your pick, drawn larger or smaller to depict a situation where we may not yet be at equilibrium. And if I'm not yet at equilibrium, this must mean I have a whole bunch more reactants on the left-hand side and not enough products on the right-hand side, so that in just a few minutes, I hope, or it depends on the rate of the reaction, of course, but after a little while, these reactants will continue to go fast toward the products, but as the products build up, then this little arrow will grow larger. And if I'm using these larger and smaller arrows to depict the proximity to equilibrium, or how close I am to equilibrium, eventually this one will get smaller and this one will get bigger, and they'll be equal in size if I was indeed using this size differential to illustrate that I'm not yet at equilibrium, as is sometimes you will see. I need a nap. Thanks for watching, guys. I'll see you in class. Yeah, I will.